This is a short video that shows some of the basic features of comprehensive meta-analysis, CMA. In order to show how the program works, I'm going to use an example of an analysis that was published by Cannon et al. You're seeing the data over here in Excel. There were a total of 4 studies. Researchers in each case recruited patients with a high level of cholesterol. They assigned them at random to either a high dose of statins or a standard dose of statins, and they recorded the number of patients in each group and the number of patients that had a cardiovascular event. The goal of the analysis was to compare the proportion of events in the high dose group versus the standard dose group. In order to run this analysis in CMA, we open up a copy of CMA. We say insert column for study names, and the program gives us a column over here. The next thing that we do is we say insert column for effect size data. Now, one of the nice things about CMA is that it allows you to enter data in almost any kind of format. It lets you work with means or proportions or correlations. And because it is so flexible, one of the first things that you need to do is to tell the program what kind of data you actually are planning to use. We have this wizard over here. I click Next. There are a number of general sets of formats. I'm going to choose the first one, which involves a comparison of 2 groups. Under that, I'm going to tell the program that I want to deal with dichotomous data, the number of events in each group. I tell the program that I'm working with prospective studies. I tell the program that I'd like to enter the number of events and sample size in each group, and then I click Finish. And as soon as I do that, the program creates a column over here for Group A, where I can enter the number of events and the total, and for Group B, where I can enter the number of events and the total. I also have the option of naming each of the groups. I'm going to call the first one the high dose group, and I'm going to call the second one the standard dose group. I also could label the kind of events, but I'm simply going to leave that as events and non-events, and I click OK. And now the program has labeled these things. So I have, for the high dose group, the number of events and the total N, and for the standard dose group, the number of events and the total N. By default, the program is going to compute the odds ratio and the log odds ratio for each study. But I'd like to work with the risk ratio, so I'm going to click risk ratio, log risk ratio, and I'm going to make that my primary effect size. I'm going to get rid of these, and I have over here now the risk ratio and the log risk ratio. The next thing I can do is to enter data for each of the studies. The first study is the Prove It study, and for the high dose group I have 147 events out of 2,099 patients. For the standard dose group, I have 172 events for 2,063 patients, and the program immediately shows me the risk ratio and also the log risk ratio, standard error, and variance. I could go ahead and enter data for the next 3 studies, but just to save a minute, I'm going to come back to Excel. I'm going to take the data over here, copy it to my clipboard, come back into CMA, click over here, paste the data in, and now I have the data for all 4 studies. The next thing I can do is I can click over here on Run Analysis, and immediately I get a forest plot that shows me the data for all 4 studies as well as the summary effect. So for example, for the first study, the risk ratio was 0.84. I see that here and I see it here. That tells me that the risk of developing a cardiovascular event in the high dose group was about 16% lower than it was in the standard dose group. The risk ratio was 0.84. That's 16% less than a risk ratio of 1. So the risk is obviously lower in the high dose group than it was in the standard dose group. While the effect in this sample was a risk ratio of 0.84, there is a certain amount of sampling error, and this tells me that in this particular study, in the Prove It study, the true risk ratio could fall any place in this range from 0.68 to 1.03, and since that range includes 1.0, since the confidence interval includes 1.0, that tells me that the effect in this study is not going to be statistically significant, and in fact the p-value for this study is 0.106. Similarly, in the second study, the risk ratio was 0.86. The confidence interval includes 1.0. The p-value is not statistically significant. In the third study, the risk ratio was 0.80. The confidence interval does not include the null. The p-value is 0.002. And finally, in the fourth study, the risk ratio was 0.89. The confidence interval, once again, does include 1.0, and the p-value is not statistically significant. More to the point, however, is what happens when we do a synthesis of the four studies. I have the option over here of working either with the fixed effect model or the random effects model. I'm going to choose the random effects model, which gives me random effect weights for computing the synthesis. On the yellow line, I have the summary effect, which is a risk ratio of 0.84 with a confidence interval of 0.78 to 0.92. I can see that over here. And what this tells me is that in the universe of studies from which these four studies were sampled, our best guess of the risk ratio was 0.85, and the confidence interval is 0.79 to 0.92. In other words, we are reasonably certain that the mean risk ratio in this universe of studies falls someplace in this range. We might also want to test the null hypothesis. In this case, the null hypothesis is that the risk of a cardiovascular event is identical for the high dose group versus the standard dose group. The z-value for that is -4.1, and the p-value is less than 0.001. And this says that we can reject the null. We can conclude that the true risk ratio in this universe is not 1.0. Rather, the high dose is actually more effective than the standard dose in preventing cardiovascular events. We can click this button over here that says Next Table to get some additional statistics. This table over here is actually divided into two parts. The left-hand side deals with the mean effect, and the right-hand side deals with the heterogeneity of the effect sizes. So if we come back here, remember a minute ago, we saw that the mean effect was a risk ratio of 0.84. We had the confidence interval and a test of the null. We see the same statistics over here. Using the random effects model, the risk ratio was 0.84. The risk ratio probably falls someplace in this range. The true risk ratio, that is, in the universe of studies. And we can reject the null. The z-value is -4. The p-value is less than 0.001. The right-hand side of this table deals with the heterogeneity of effects. What we're looking at over here are the observed effects, and we see a little bit of dispersion in the effect size. It ranges from about 0.84, 0.86, 0.80, 0.89. These are reasonably consistent, but these are the observed effects. The question would be, and some of the dispersion that we're seeing over here might be due to differences in the true effects, but some of it is certainly due to random sampling error. And the question would be, if we could get rid of that sampling error, would there still be any evidence of dispersion, and how much dispersion would there be? That is addressed by the statistics over here. In this case, we have a Q value in the degrees of freedom. The Q value is less than the degrees of freedom, which tells us that the amount of dispersion that we're seeing over here in the observed effects is actually less than we would expect to see based purely on the sampling error. And therefore, there's no evidence over here that the true effects actually vary at all. Whenever the Q value is less than the degrees of freedom, there's no need to test the significance of the heterogeneity because there is no evidence of any heterogeneity. It follows that I square, which is the proportion of the dispersion that is probably due to true effects rather than sampling error, is 0%, and our estimate of the variance in true effects, which is tau square, is also going to be 0. One other thing we might want to do over here is to create a high resolution plot. I can do that by simply clicking on the button that says high resolution plot, but before doing that I'm going to customize the display a little bit just to make it a little bit neater. I'm going to get rid of the z-value because we really don't need that. I'll click high resolution plot. And what we see over here is that we have a plot that we can now send over to Word and include it as part of our document. I can edit any part of this if I want to. I can change the colors. For example, I could change the colors and make them for slides, and then send this over to PowerPoint as well. So this is a quick look at some of the more basic features of the program. I invite you to go to our website, metaanalysis.com, and if you click on Support and Video Tutorials, you'll see that there are other videos that show you how to work with other effect sizes, how to do more advanced analyses, for example, analyses that compare the effect size in different subgroups of studies, or analyses that use meta-regression, or that look at publication bias, or that work with more complex data structures. Finally, for those who might be interested, we're offering a series of 3-day workshops on meta-analysis. These are listed on a different website. This would be www.metaanalysisworkshops.com, and I hope you'll have a look at that. If you have any questions, my email is michael@metaanalysis.com, and I'd be very happy to hear from you. Thank you.